Welcome, ladies and gentlemen. My name is Brian McLogan, and in this video, we are going to work on what you need to know for applications in trigonometry. So this is their next unit inside of our pre-calculus course, and what I did is I designed some problems that are very common that students come up with that they either kind of get stuck or they kind of forget how to do it. So I wanted to kind of create some questions just to remind some students of some foundational problems that I think will help them as we work through our chapter on applications in trigonometry. So for example, the first coming to 4 questions just kind of deal with solving for x and y using some angle relationships with parallel lines, right angles, and then also using within triangles or right triangles, and just kind of understanding those relationships between the angles from there. And then we're going to work on evaluating the missing side of a triangle using trigonometric functions. And then we're going to finding inverse trigonometric functions. Then we're going to use our trigonometric functions. I'm sorry, that's correct. So sorry, for the last one, we're going to use our trigonometric functions to find the missing side. And then for here, we're going to use our inverse trigonometric functions to find the angle. And then we're going to go ahead and work on some coordinate point geometry and find the distance as well as the slope between 2 points. And that'll be it. So let's go ahead and get started here. So the main important thing, there's so many angle relationships when we have parallel lines and a transversal, right? We have parallel lines and transversal. Just to kind of name a few, we have alternate interior, alternate exterior, corresponding angles, same side interior. There's a lot of those definitions that we're going to want to remember. And obviously, I don't want to go through all of them for each one, but we'll kind of remember a couple of these, and I'll just kind of go through that. So first of all, if this is 43 degrees, now I can recognize that this x here is going to be 43 degrees as well, because those are vertical angles, if you remember that from vertical angles portion. All right. So if that's 43 degrees, now we can kind of play around with this, right? So we can say that this is also 43 degrees because these are alternate interior angles, or you could also say these two angles are corresponding angles. And then you can see 43 plus y, those are going to be that supplementary. The same thing, also x and y are what we call same side interior, and x, therefore same side interior are going to be supplementary as well. So there's a lot of different ways we could go ahead and solve this. You can use the idea of just using vertical angles and then knowing the same side interior. You could use alternate interior and knowing that 43 degrees and y represent 180 degrees. So a lot of different ways to kind of show this. Obviously, if I have 43 degrees now for x, therefore, I'll just subtract 43 degrees on both sides, and I get 137 degrees is going to be y. So just another reminder, like x could be there, that would be y, that would also be to y, and that would be y. So a lot of different definitions. Actually, I'm just going to write those in there. So we have alternate interior. Remember, those are the same. We have alternate exterior. Those are the same. And we have vertical angles. Let's actually review that. That's actually a good idea. Vertical angles. So those are all the same. Now the ones that are supplementary, and also corresponding. Okay, there you go. Those are all the same. When you have those angles, those are equal to each other. So make sure that you remember those and know how to label them. The next ones, the ones that are supplementary, are going to be same side interior. And obviously, if they're going to be same side interior, or if they obviously are right next to each other, those are going to be supplementary, and that's right. So those are supplementary. Okay, so just a quick little review from there. Now, the next one here is if we recognize this is 90 degrees, this is very important, because if this is 90 degrees, then that means that obviously has to be 90 degrees as well. So therefore, x plus y add up to 90 degrees. So I can write the equation x plus y is equal to, not 180, they're equal to 90 degrees, because when you have two angles that add up to 90 degrees, those are what we call corresponding angles. And in this case, I know x is going to be 37 degrees. Oops. So that's going to be x plus 37 equals 90. And now let's just go ahead and subtract. So therefore, x in this case is going to equal, let's see, 53. 53 degrees. Now, so I know that that's 53 degrees. Now, you could obviously go ahead and say, well, if that's 90, then this also has to be 90, right? And again, that's the point. Like, if you recognize you have two intersecting angles that create 90 degrees, that means all of these are going to be 90 degrees. And you could also use vertical angles as another way to justify that. But we can just say 90 degrees here is going to be the y. So there's a lot of relationships we want to remember. And when we're looking at, some problems where we have parallel lines, immediately our brain wants to think of all of those relationships. So it's a good thing just to review those. There's at least one example where I kind of talked about, what those different side lengths are or how to do it. All right, so now let's kind of get into the triangles. So again, we have this 163 and x that adds up, that gives you a straight line, right? So therefore, those are supplementary. So I can just say x plus 163 degrees is 180 degrees, right? They create a straight line. So therefore, just subtract here. That's going to be x is going to equal 17 degrees. Now, the next thing is we could use the interior angle sum theorem. And the interior angle sum theorem for a triangle says that all the angles in a triangle add up to 180. So we have 17 degrees plus 90 degrees, right? That box represents 90 degrees, plus y, we'll just say y, equals 180 degrees. Well, 90 plus 17 is 107 degrees, plus y equals 180 degrees, and therefore y is just going to equal 73 degrees, okay? All right, now the last one, again, we can recognize here that just using vertical angles, right? Whenever you have two intersecting angles or two intersecting lines, opposing angles of that vertex are going to be equal. So therefore, we can just say x equals 67 degrees. I forgot to write that these were parallel lines. My bad. And since these are going to be parallel lines, we can see that actually these are going to be corresponding angles. So these are an example of corresponding angles. And again, remember, corresponding angles are actually the corresponding angles are equal as well. So therefore, we can say y is going to equal 67 degrees. Now, I didn't ask for this angle, but now we could recognize that that is 90. And we could also figure out what that angle is, again, if we wanted to. Let's just call this, z or something. You could also go and figure that one out just if you wanted to. Z plus 90 degrees, plus 67, right, equals 180. And that would be 157. Z equals, I don't know why I'm doing this. I didn't ask for this, but I just wanted to, I guess, play around with this. So that'd be 157 degrees equals 180 degrees. That's 180 degrees. And then subtract, that's going to be 23. So z equals 23 degrees. So just to have a little fun, do a little extra work. Didn't ask for it, but let's have fun. All right, the next one is use a calculator to find the missing side of a triangle. So I have my nice little calculator. You could either use a graphing calculator or really just a scientific calculator, whatever you have. But notice that 31 degrees, we're not familiar with any angle or point on the unit circle at an intersection of 31 degrees. So that's why we're going to want to use our trigonometric functions. Now, with whatever calculator you're using, though, remember our angles could either be in degrees or radians. So we're going to want to make sure that your calculator is set in degree mode if you are using your trigonometric functions for degrees, which in applications of trigonometry, almost all the problems, 99.9% of the problems are all going to be in degree mode. So we'll basically just have our calculator in degree mode and not have to worry about switching it. However, we just want to be aware if something does happen to be in radians, that we just make sure that we change the mode in the calculator. All right, so to do these types of problems, the main idea is, we know that for our trigonometric functions are based on the sides of an angle, but they're always of an angle, right? So it's based on the angle, and then it's a comparison of the sides. So I see that based on this angle here, the sides that I'm comparing is the opposite side and the hypotenuse. So I think which trigonometric function deals with comparing the opposite and the hypotenuse, and that's going to be the sine. So I can write the sine of 31 degrees, sine of 31 degrees, is equal to x over 5. And basically, again, it's saying when you have a triangle with an angle of 31 degrees, how big is the opposite side compared to the hypotenuse? We know it has to be smaller, right? So if we, but we don't know where it's going to be at. So all we need to do is solve for x. So to do that, we're just going to multiply by 5 on both sides. And then we get x equals 5 times the sine, and I'm sorry, my 5's and s's look the same, of 31 degrees. All right, and I'm just going to, let's see, we're just going to, I'll probably round this to the nearest 10th. I didn't actually write that in there, so let's just do to the nearest 10th. All right, so I'm just going to type in 5 times the sine of 31. And I get 2.57, and rounding that, that'll be x equals 2.58 as I round to the nearest 10th. Okay, and again, like, therefore, that's what x is going to equal. That is what that side length is for. Now, in the next one, we again have 31 degrees, but you recognize that now we have the adjacent side and the hypotenuse. And again, we're actually not looking for the adjacent side. Now we're actually looking for the hypotenuse. But again, like, which trigonometric function deals with the adjacent side and the hypotenuse? Well, that's going to be cosine. So we'll write a statement, cosine of 31 degrees is equal to adjacent over hypotenuse. Now this one, again, just like here, we want to get the 5 off the denominator, right? Well, because we got to solve for x. Well, we can't solve for x when x is in the denominator. So the first thing we have to do is multiply by x on both sides. That's going to give us an x times the cosine of 31 degrees is equal to 4. Now again, to solve for x, I need to divide by the cosine of 31 degrees. So therefore, x equals 4 over the cosine of 31 degrees. Now again, that's where we're going to type into my calculator, and I'll round. So 4 divided by the cosine of 31 degrees is going to be 4.67 as you round. And again, that makes sense. Again, in the context of the triangle, we know it has to be bigger than 4, right? Because it's the hypotenuse, it's the largest side. All right, the next one is, now we can see we have the opposite over the adjacent. So we can just write, tangent of 31 degrees equals x over 2. And hopefully we start to get really good at this. We don't need to show our work. And we say, oh, okay, x is equal to 2, tangent of 31 degrees. And that's just what we're going to plug into our calculator. So 2 tangent of 31. And that ratio is going to be 1.2. And then last but not least, here's this one. So we write tangent of 31 degrees equals 3 over x. Well, again, now if we were to multiply x and then divide by tangent of 31, we get x equals 3 over the tangent of 31 degrees. So that's why we're kind of doing these problems, you can see obviously in the first two problems, I kind of worked them out. You could see my math, but obviously as we start to get to these, we can start doing that hopefully a little bit quicker. 3 divided by tangent of 31, and that's going to be 4 or just 5 actually, as we round. So x is going to equal 5. As we round to the nearest 10th, that just rounds up to the nearest whole. Okay, so that's how we use our trigonometric functions to find a missing side of an angle. But we have to remember, if we're looking for the missing angle, we need to use our inverse trigonometric functions. Now, use the calculator to find the missing triangle from on there. Okay, so, but again, yeah, this is what I was thinking of. Since we're only dealing with triangles, we don't have to worry. We don't have to worry about the restrictions, because our calculators already has those restrictions based in there. But we do need to kind of understand this concept of those angles with a triangle to make sure that they are going to make sense, which we'll kind of get to in some problems. But either way, we have the missing side of the angle. So we're just going to use our trigonometric function. In this case, we have opposite over hypotenuse, so that's going to be sine. So we could say sine of theta is equal to 2 over 4. Well, in reality, if I want to solve for theta, I'm going to say theta equals the sine inverse of 1/2. Now, the nice thing about this one is I don't even actually need to use a calculator for this. I'm basically saying, the sine of what angle is equal to 1/2. Well, I know that by the unit circle, right? I know x equals 1/2 at 30 degrees. So in this case, I'm going to use 30 degrees. And when we were in our first unit, in our trigonometry unit, I always said we're going to use the inverse to be able to use radians. But it's more common to use degrees in this chapter. So therefore, I'm just going to use 30 degrees. And again, you can check your work. Sine of 30 degrees is equal to 1/2. All right. For the next one, we have opposite over adjacent. So that's going to be tangent. So I just say the tangent of theta is 3 over 2, but we don't really need to get to that point. We can just say theta equals tangent inverse of 3 over 2. So now I'm just going to do tangent inverse of 3 over 2. And we get 56.3 degrees. So 56.31. There you go. And then the last one you can see here is the cosine, because we're going to use the adjacent over the hypotenuse. So in this case, I'm just going to say theta equals cosine inverse of adjacent over hypotenuse. So I can get immediately right into the inverse trig function. I don't need to write the statement first and then rewrite it. You can just get right into there. So cosine inverse of 6 divided by 7. And that's going to be 31 degrees. So theta is equal to a 31 point, just 31. As it rounds to the nearest whole. And again, those are degrees. So we're going to want to make sure we use degrees from that case. So that's basically kind of the difference here. Remember, when we're using our inverse trig functions, we're trying to find the angle from on there. So again, we're basically doing the inverse trig of a ratio of the sides to find that missing angle. And again, since we're dealing with a triangle, it's going to make sense to be using degrees rather than using radians. All right, last question here is find the missing information given the points. So I have a point 1, 1, which we called A, and another point B, which we have as 5, 3. So we need to find the distance, and we need to use the slope. So there's a couple different ways we could do this. I think the first thing we should just do anyways is just plot the points. So let's just get a good visual of what's actually going on here. So I have 1 point, 1, 1, which is A. And then I have another point B, which is at 1, 2, 3, 4, 5, 1, 2, 3. And let's call it point B. So I need to basically figure out the distance from A to B as well as the slope. Now, what I like to be able to kind of figure out there's a couple different ways. There are those formulas, if you remember the formulas. There is a distance formula and there is a slope formula. But, when we learn slope and distance, one of the things that we learn though is also like using the slope triangle. And I think just by going from using a slope triangle, by creating this triangle here, we can see that the distance from A to B is 1, 2, 3, 4. And from vertical distance is 1, 2, right? So if I really just wanted to find the distance AB, I know that's just going to equal the square root of 4 squared plus 2 squared. Well, 4 squared plus 2, so 4 squared is 16 plus 2 squared is going to be 4. So that's going to be square root of 20. And therefore, we could rewrite that as a decimal. We'll have calculators in this one. So why don't we actually just figure that out? Square root of 20. Let's round to the nearest tenth. And that's going to be 4.47. Okay, and I'll get to the formal definitions here in a second as well, because sometimes just you drawing the triangle might not be necessary or might not be as easy as it is for this problem. To find the slope, remember the slope is the change in the y over the change in the x. So if I just want to find the slope of AB, I just need to say, well, how far is it changing vertically? Well, that's 2. How far is it changing horizontally? That's 4, right? So therefore, you can just see that's going to be 1/2. Now, let's say your points are not as nice as these. And so what we're going to want to do then is just label these as x1, y1, and this point as x2 and y2. All right, so if we just label those coordinate points, and again, the reason why I'm using the subscript is just to differentiate between the x's for the first point and the second point. And it doesn't matter how you label them, just make sure you're consistent with x1, y1 and x2, y2. And again, because some problems in this section might be more difficult than others. So it's just important to remember the distance formula between any 2 points is the square root of, and again, we could say this as d, right? Because really it's d squared equals 4 squared plus 2 squared, right? And that's why I got d equals the square root of 4 squared plus 2 squared. Yep. But anyways, the formal definition of the distance formula is the change in the horizontal distance. So that's going to be x2 minus x1, quantity squared, plus the change in the vertical distance, y2 minus y1 squared. And that's basically what I did. I basically said what does this change horizontally, which was 4, and what was the change vertically. So I always prefer to graph it if possible, but remember, sometimes that's not the case. Now the slope is very similar, because really you're just going to take the change in the y coordinates, y2 minus y1, over the change in the x coordinates, x2 minus x1. And that's basically what we did there. We found the change in the y coordinates was 2 and the change in the x coordinate was 4. And then we just write that as a ratio. And there you go, ladies and gentlemen. That is basically some problems to kind of get you started for applications of trigonometry. So as far as dealing with the distance, the slope, and then how to use inverse trigonometric functions, how to use a calculator for our trigonometric functions, as well as how to use our relationships of angles in triangles, as well as with parallel lines. So I hope that helps, and I look forward to helping you out in this chapter. Cheers.